We humans love patterns. Patterns give us a sense of predictability and control in an otherwise chaotic world. We seek them out in the chaos of the universe, finding order in the seemingly random. This quest for order is what drives much of our scientific inquiry and daily decision-making. One such pattern, the normal distribution, emerges time and again in the natural world. It's a fundamental concept in statistics and probability theory. Picture a bell, its smooth curve a familiar sight. This bell-shaped curve is not just a mathematical abstraction, it's a reflection of how many natural phenomena behave. This is the shape of normality. The bell curve, or Gaussian distribution, is a powerful tool for understanding the world around us. This elegant curve, also known as the Gaussian distribution, describes the tendency for data to cluster around an average value. It's a cornerstone of statistical analysis. Imagine measuring the heights of all the students in a school. You'd find that most students are of average height, with fewer students being exceptionally tall or short. Most students would fall near the average height, with fewer individuals at the extremes of very tall or very short. This clustering around the average is a hallmark of the bell curve. This pattern extends beyond the classroom. It's a universal principle that applies to many aspects of life and science. From the variation in star brightness to the distribution of blood pressure readings, the bell curve makes its presence known. It's a versatile tool used in various fields of study. The normal distribution provides a powerful tool for understanding and predicting the behavior of data in countless fields. It helps us make sense of complex data sets and draw meaningful conclusions. But like any model, the normal distribution has its limitations. It's not a one-size-fits-all solution. Not all data conforms to this elegant shape. Some data sets have skewed distributions, heavy tails, or multiple peaks. We must venture beyond the familiar bell curve to explore the rich tapestry of data distributions that exist in our universe. By doing so, we gain a deeper understanding of the complexities and nuances of the world around us. Every bell curve has a unique story to tell. Two key characters in this fascinating story are the mean and standard deviation. The mean, often represented by the Greek letter mu, marks the center of the distribution. It's the average value around which the data congregates and clusters. The standard deviation, denoted by the Greek letter sigma, measures the spread or dispersion of the data. A large standard deviation indicates a wider spread of data points, like a bell curve that's been gently flattened. A small standard deviation, on the other hand, suggests a tighter clustering of data around the mean, like a tall and narrow bell. These two parameters, the mean and standard deviation, work in tandem to define the shape and characteristics of a normal distribution. They provide a concise summary of the data, allowing us to quickly grasp its central tendency and variability. The bell curve may appear as a single entity, but it represents a family of infinite variations. Each curve tells a unique story about the data it represents. By adjusting the mean and standard deviation, we can create a multitude of normal distributions, each with its unique characteristics. These adjustments allow us to model different real-world phenomena accurately. Shifting the mean, for example, moves the entire curve along the x-axis without altering its shape. This shift can represent changes in average values over time or between different groups. Imagine two bell curves representing the heights of students in two different schools. The differences in their means can provide insights into the average height differences between the two populations. The school with taller students would have a bell curve shifted to the right, reflecting a higher average height. This visual representation makes it easier to compare and understand the data. Changing the standard deviation, on the other hand, affects the spread of the curve. This change can indicate the level of variability or consistency within the data set. A larger standard deviation results in a wider, flatter curve, indicating greater variability in the data. This means that the data points are more spread out from the mean. A smaller standard deviation leads to a taller, narrower curve, signifying less variability. Here, the data points are clustered more closely around the mean. Despite these variations, all members of the normal distribution family share certain fundamental properties. These properties make them a powerful tool in statistical analysis. They are symmetrical, bell-shaped curves with a single peak at the mean. This symmetry is a key feature that helps in identifying and interpreting normal distributions. Understanding these properties is essential for interpreting data and making informed decisions. Whether in academic research, business analytics, or everyday problem solving, The normal distribution provides a foundational framework for understanding variability and central tendencies in data. The allure of the bell curve is undeniable, but not all data conforms to its elegant shape. The bell curve, or normal distribution, is often seen as the gold standard in statistics, representing a perfect balance where most data points cluster around a central mean. However, real-world data is rarely this tidy. The universe is a messy and complex place filled with data that defies simple categorization. In reality, data can be influenced by countless variables, each adding its own layer of complexity. This complexity often results in data that doesn't fit neatly into the bell curve. Some datasets exhibit skewness, with a longer tail on one side of the distribution. This skewness can be caused by outliers or a natural asymmetry in the data. For example, income distribution often shows a right skew, where a small number of individuals earn significantly more than the majority. Others may have multiple peaks or outliers that deviate significantly from the norm. These multimodal distributions can occur in datasets that combine different populations or categories. For instance, test scores from different schools might show multiple peaks if the schools have varying levels of performance. Consider categorical variables, which represent qualities or categories rather than numerical values. These variables are often used in social sciences and market research to classify data into distinct groups. Examples include gender, hair color, or type of animal. These categories are qualitative and do not have a natural order or numerical value, making them unsuitable for bell curve representation. These variables do not lend themselves to a bell curve representation. Instead, they are often visualized using bar graphs or pie charts, which can clearly show the frequency or proportion of each category. Discrete variables, which can only take on specific values like the number of children in a family, also fall outside the realm of the normal distribution. These variables are countable and finite, and their distributions are often represented by histograms. These variables are often represented using bar graphs or histograms, which highlight the distinct categories and their frequencies. This method of representation helps in understanding the distribution and frequency of each specific value. Furthermore, some variables have inherent limits. These limits can restrict the range of possible values, leading to distributions that are not symmetrical. For instance, the percentage of correct answers on a test cannot exceed 100%. This upper limit can cause a left skew in the distribution of test scores, especially if many students perform well. These limits can result in skewed distributions that deviate from the symmetrical bell curve. Recognizing these skewed patterns is essential for accurate data analysis and interpretation. Recognizing these departures from normality is crucial for choosing appropriate statistical methods and interpreting results accurately. By understanding the nature of the data, researchers can select the right tools and techniques to analyze it effectively, ensuring that their conclusions are valid and reliable.